Hello all, in this video we will look at the backtracking step size selection method for gradient descent. We begin with pondering over the step size selection method in gradient descent. Recall that we obtained that the oracle complexity of gradient descent when using a constant step size of eta equal to 1 over L was t is equal to BL by 2 epsilon. Of course, the oracle complexity remains of the same order if we change the step size around 1 over L. But this approach still requires the knowledge of L. There are two common issues with such algorithms. First is that L may not be known. If you are given a complicated objective function in high dimensions, there is no efficient numerical method to estimate L. Second, L obtained from the standard definition may just be too high. So for this, suppose that there is a function whose Hessian norm is large when x is large and small when x is small. So let me plot the norm of the Hessian as a function of the norm of x. That is, for this function, suppose that the Hessian norm increases with increasing norm of x. Now by definition, L is the maximum of the Hessian norm. So L will be large, it will be equal to the largest value of the Hessian at any x. So the bounds like quadratic upper bound will be very loose. But we still want to use gradient descent or similar algorithms. In most practical problems, it would often be the case that while things get unbounded for large x, the optimum does still occur at a small x. Further, we would be able to select an initial x1 that also has a small norm. So in other words, it is very likely that the iterates x1, x2 that are all generated by gradient descent are restricted to this region where norm of x stays small. So in such a scenario, it is unlikely that we will ever encounter a very large x while running the gradient descent algorithm. So these are the two reasons why we do not want the step size to be a function of L. So let us consider the problem of selecting eta. Recall that if L is large and we choose eta equal to 1 over L, it would be very small, and this would definitely result in very slow progress. The main reason we are using large L is so that we have the quadratic upper bound property that would imply that the sequence f of xt is non-increasing. So what if there was a method that would ensure that the function value would be decreasing while allowing us to choose eta that is greater than 1 over L for each t? You can think of it as selecting an eta t that would only be valid around the current iterate xt. So you can think of it as a new perspective of looking at the algorithm design, the key idea being that we try to avoid using L in the algorithm and instead design the algorithm such that it works without knowing L. The algorithm should adapt to the problem parameters like L. The class of algorithms is called the adaptive step size algorithms. We will look at very simple adaptive step size algorithm called the backtracking line search method. There are many other line search methods as well. All of these algorithms try to find the optimal step size so as to ensure that a certain amount of progress occurs without ever using L. So let us look at the backtracking line search algorithm. We consider the following version of the gradient descent: xt plus 1 equal to xt minus eta t times gradient f of xt. We observe that eta t is dependent on t. The main idea is that we will carefully select eta t so as to guarantee a certain level of decrement in the function value. For this purpose, we will perform a line search over eta t so as to get the value that gives us the required amount of decrement. We will use the following approach to select eta t. So we will initialize eta t of 1 equal to 1. So there is nothing special about this 1 here, but this quantity should not be too small. Then we will repeat the next two steps. So at the kth step, we will check this condition and we will break if this is true. So we will break if f of xt minus eta t k gradient f of xt is less than f of xt minus alpha times eta t k norm square of gradient f of xt. So if this condition is true, we will break. Otherwise, we will decrease eta t as eta t of k plus 1 equal to beta times eta t of k, where beta is some quantity that is less than 1. And continue. So this is a line search routine that must occur at every iteration. Observe that there are two parameters in this subroutine, alpha and beta, and both can be tuned in practice such that the algorithm works. For our discussion, we can just take alpha equal to half and beta is some constant that is less than 1. And the final result will depend on beta and L. A similar analysis can be carried out for arbitrary alpha and beta values. A remark about the working of the algorithm. The algorithm requires us to calculate fx many times. This was not required earlier. For instance, the gradient descent algorithm, the oracle gives us the gradient and we are done. But here we are additionally requiring access to the values of f of x at any x. So practically this kind of algorithm requires that calculating f of x should be inexpensive. Let us begin by trying to get some intuition as to what is going on in this line search. In the first step, we are choosing eta t to be a large value, in this case 1. As we said, nothing special about 1, it is just have to be some sufficiently large value. Then we are checking if the choice allows us to have a sufficient decrement. If not, we are adjusting eta t by decreasing it since beta is less than 1. So next time we try with a smaller step size. The procedure continues till we get to a point where there is sufficient decrement in the function value. Assuming that we start with a sufficiently large value, we will always end up at a point that achieves sufficient decrement. So this property we will show theoretically. Let us look at our earlier example of the contour plot for illustrating this idea. Let us say that the current iteration t, we are at a given point xt. Now our starting value of eta t is a large value of 1. So if we were to update xt using eta t equal to 1, we would end up too far ahead. Basically, the step size is so large that we are overshooting and ending up at a point where the function value is even larger than what it was at xt. So that is what happens if you choose a very large step size. The gradient descent algorithm goes haywire and diverges in that case. Then the backtracking routine kicks in and we multiply the current value of eta by a factor of beta, which is less than 1, say 0.7, 0.8. So if the initial value of eta was 1, now it becomes equal to beta. So next we try with a reduced value of eta, which is now 0.7 or 0.8, and check where we end up. So this smaller value of eta is much better. At least the function value here is not increasing, but the decrement in the function value is not that much. So this value still results in some overshoot and only a small decrement. Next, we can try with even smaller value of eta, that is, we multiply the current value of eta again with beta. So now the step size becomes beta square. So if beta was 0.7, then beta square will be 0.49. Next, we try with eta equal to beta square and we calculate the function value and find out that it is now much less. So if this much decrement is acceptable, then we are fine and we can stop the line search and go to iteration t plus 1. Otherwise, we can continue the iteration. So in this figure, it seems that it might be good to continue further. We will probably get very close to the optimum, but in general, we do not know the optimum. So the entire question is about selecting the parameters beta and alpha so as to ensure that the process works every time for every possible starting point and for every possible function that we encounter. Our analysis will in fact reveal that. So that is all for this video. We will carry out an analysis of the backtracking line search in the next video.